Atoms are made in the insides of stars. In most of the stars we see, hydrogen nuclei are being jammed together to form helium nuclei. Every time a nucleus of helium is made, a photon of light is generated. This is why the stars shine. Stars are born in great clouds of gas and dust, like the Orion Nebula, 1,500 light years away, parts of which are collapsing under gravity. Collisions among the atoms heat the cloud until, in its interior, hydrogen begins to fuse into helium, and the stars turn on. Stars are born in batches. Later, they wander out of the nursery to pursue their destiny in the Milky Way. Adolescent stars, like the Pleiades, are still surrounded by gas and dust. Eventually, they journey far from home. Somewhere, there are stars formed from the same cloud complex as the Sun, 5 billion years ago. But we do not know which stars they are. The siblings of the Sun may, for all we know, be on the other side of the galaxy. Perhaps they also warm nearby planets, as the Sun does. Perhaps they too have presided over the evolution of life and intelligence. The Sun is the nearest star, a glowing sphere of gas, shining because of its heat, like a red-hot poker. The surface we see in ordinary visible light is at 6,000 degrees centigrade. But in its hidden interior, in the nuclear furnace where sunlight is ultimately generated, its temperature is 20 million degrees. In X-rays, we see a part of the Sun that is ordinarily invisible, its million-degree halo of gas, the solar corona. In ordinary visible light, these cooler, darker regions are the sunspots. They are associated with great surges of flaming gas, tongues of fire, which would engulf the Earth if it were this close. These prominences are guided into paths determined by the Sun's magnetic field. The dark regions of the X-ray Sun are holes in the solar corona, through which stream the protons and electrons of the solar wind on their way past the planets to interstellar space. All this churning power is driven by the Sun's interior, which is converting 400 million tons of hydrogen into helium every second. The Sun is a great fusion reactor into which 1 million Earths would fit. Luckily for us, it's safely placed 150 million kilometers away. It is the destiny of stars to collapse. Of the thousands of stars you see when you look up at the night sky, every one of them is living in an interval between two collapses. An initial collapse of a dark interstellar gas cloud to form the star, and a final collapse of the luminous star on the way to its ultimate fate. Gravity makes stars contract unless some other force intervenes. The sun is an immense ball of radiating hydrogen. The hot gas in its interior tries to make the sun expand. The gravity tries to make the sun contract. And the present state of the sun is the balance of these two forces, an equilibrium between gravity and nuclear fire. In this long middle age between collapses, the stars steadily shine. But when the nuclear fuel is exhausted, the interior cools, the pressure is no longer enough to support its outer layers, and the initial collapse resumes. There are three ways that stars die. Their fates are predestined. Everything depends on their initial mass. A typical star with a mass like the sun will one day continue its collapse until its density becomes very high. And then the contraction is stopped by the mutual repulsion of the overcrowded electrons in its interior. A collapsing star twice as massive as the sun isn't stopped by the electron pressure, and it goes on falling in on itself until nuclear forces come into play, and they hold up the weight of the star. But a collapsing star 3 times as massive as the sun isn't stopped even by nuclear forces. There's no force known that can withstand this enormous compression. And such a star has an astonishing destiny. It continues to collapse until it vanishes utterly. So every star is characterized by the force that holds it up against gravity. A star that's supported by the gas pressure is a normal run-of-the-mill star like the sun. A collapsed star that's held up by electron forces is called a white dwarf. It's a sun shrunk to the size of the Earth. A collapsed star supported by nuclear forces is called a neutron star. It's a sun shrunk to the size of a city. And a star so massive that in its final collapse it disappears altogether is called a black hole. It's a sun with no size at all. But on their ways to their separate fates, all stars experience a premonition of death. Before the final gravitational collapse, the star shudders, briefly swells into some grotesque parody of itself. With its last gasp, it becomes a red giant.
Some 5 billion years from now, there will be a last perfect day on Earth. Then the sun will slowly change and the Earth will die. There is only so much hydrogen fuel in the sun. When it's almost all converted to helium, the solar interior will continue its original collapse. The higher temperatures in its core will make the outside of the sun expand, and the Earth will become slowly warmer. Eventually, life will be extinguished, the oceans will evaporate and boil, and our atmosphere will gush away to space. The sun will become a bloated red giant star, filling the sky, enveloping and devouring the planets Mercury and Venus, and probably the Earth as well. The inner solar system will reside inside the sun. But perhaps by then, our descendants will have ventured somewhere else. In its final agonies, the sun will slowly pulsate. By then, its core will have become so hot that it temporarily converts helium into carbon. The ash from today's nuclear fusion will become the fuel to power the sun near the end of its life in its red giant stage. Then the sun will lose great shells of its outer atmosphere to space, filling the solar system with eerily glowing gas, the ghost of a star outward bound. Perhaps half the mass of the sun will be lost in this way. Viewed from elsewhere, our system will then resemble the Ring Nebula in Lyra, the atmosphere of the sun expanding outward like a soap bubble. And at the very center will be a white dwarf, the hot, exposed core of the sun, its nuclear fuel now exhausted, slowly cooling to become a cold, dead star. Such is the life of an ordinary star, born in a gas cloud, maturing as a yellow sun, decaying as a red giant, and dying as a white dwarf enveloped in its shroud of gas. Suppose, as we traveled through interstellar space in our ship of the imagination, we could sample the cold, thin gas between the stars. We would find a great preponderance of hydrogen, an element as old as the universe. We would find carbon, oxygen, silicon. The most abundant atoms in the cosmos, apart from hydrogen, are those most easily made in the stars. But we would also find a small proportion of rare elements, praseodymium, say, or gold. They're not made in red giants. Such elements are manufactured in one of the most dramatic gestures of which a star is capable. A star more than about 1.5 times the mass of the sun cannot be a white dwarf. It may end its life by blowing itself up in a titanic stellar explosion called a supernova. There has been no supernova explosion in our province of the galaxy since the invention of the telescope, and our sun will not become a supernova. But in our imagination, we can fulfill the dream of many earthbound astronomers and safely witness, close up, a supernova explosion. Most of stellar evolution takes millions or billions of years, but the interior collapse that triggers a supernova explosion takes only seconds. Suddenly, the star becomes brighter than all the other stars in the galaxy put together. If a nearby star became a supernova, it would be calamity enough for the inhabitants of this alien system. But if their own sun went supernova, it would be an unprecedented catastrophe. Worlds would be charred and vaporized. Life, even on the outer planets, would be extinguished. In our ship of the imagination, we are now backing away from the star. But the explosion fragments, traveling almost at the speed of light, are overtaking us. Individual atomic nuclei, accelerated to high speeds in the explosion, become cosmic rays. This is another way that stars return the atoms they've synthesized back into space. The shockwave of expanding gases heats and compresses the interstellar gas, triggering a later generation of stars to form. In this sense also, stars are phoenixes, rising from their own ashes. The cosmos was originally all hydrogen and helium. Heavier elements were made in red giants and in supernovas, and then blown off to space, where they were available for subsequent generations of stars and planets. Our sun is probably a third-generation star. Except for hydrogen and helium, every atom in the sun and the Earth was synthesized in other stars. The silicon in the rocks, the oxygen in the air, the carbon in our DNA, the gold in our banks, the uranium in our arsenals were all made thousands of light years away and billions of years ago. Our planet, our society, and we ourselves are built of star stuff.